Hello, this is Dr. Christy Patton-Lukes, a chemical engineering professor at Missouri S&T. This video lesson will be looking at ideal gas mixtures. In particular, we'll be defining and using thermodynamic properties for ideal gas mixtures. So, an ideal gas is one that satisfies the relation PV equals nRT. Generally, this is appropriate as the pressure approaches zero, and it's a better estimate for small round molecules that aren't going to interact with each other. So now then we want to extend this to an ideal gas mixture. An ideal gas mixture also must satisfy PV equals nRT, where N is the sum of the number of moles of a variety of components. Again, this is still going to be best as pressure approaches zero. All the molecules still need to be small and round, and none of the molecules can interact with each other. And this needs to apply even for like species A with species B. Now, this is never going to be true. It's never true that we have an ideal gas. An ideal gas mixture is even more unlikely. But it is a great reference state, and so therefore we use it frequently as a reference. In this lesson, we're going to begin looking at properties of these ideal gas mixtures. Now, first let's look at partial molar volume, partial molar internal energy, and partial molar enthalpy of an ideal gas mixture. For these are simply taking the specific volume of each species and adding these up, or the specific internal energy of each species times the number of moles of each species and adding them up, or the same thing with enthalpy. If that's the case, then when you apply the rules for partial molar quantities, then I'm going to take the derivative with respect to n sub I for each one of these. And what I'm left with is simply the specific, for component I end up with the partial molar volume is the specific volume of that substance as an ideal gas. Internal energy for the component in an ideal gas mixture is the specific internal energy of that component as an ideal gas. And the partial molar enthalpy of an ideal gas, of a component in an ideal gas mixture, is simply the enthalpy of that component as an ideal gas. But this isn't going to be true in general. Next, let's define partial pressure. You've probably seen this before. Partial pressure is the mole fraction times the total pressure. For an ideal gas mixture, Xi is the number of moles of the species divided by the total number of moles. But the pressure, if it's an ideal gas mixture, is the total number of moles times RT over V. The sum of the number of moles, the total number of moles, will cancel top to bottom, and so I'm left with the number of moles of the species times RT over V, which simply means that the partial pressure for a species in an ideal gas mixture is the pressure that an ideal gas with the same number of moles would take up in that total volume. Why did we need this? Well, let's look at some of those other partial molar properties. One way to think of a partial molar property other than volume is that it's equal to the corresponding molar property of the species as a pure ideal gas at the mixture temperature and at a pressure equal to its partial pressure in the mixture. And I guess that applies for volume, but it also applies for internal energy and enthalpy because for an ideal gas, those are independent of pressure. But what about entropy? Entropy is a function of pressure. We've seen that ds is Cp dt minus R over P dP. It's a function of both temperature and pressure. So therefore, the difference between the partial molar and the specific entropy for an ideal gas mixture and an ideal gas will be that minus R ln of Pi over P. But by the definition of partial pressure, that's just minus R ln of xi. Now, you may have seen this derived in a different way using statistical mechanics in some of your other courses. Once we have this definition, we can now extend our definition of Gibbs energy by looking at G as the definition of H minus Ts. If I want to again see what's the difference between the partial molar Gibbs energy for an ideal gas mixture and the specific Gibbs energy for an ideal gas for species I, I'm going to have the change in H minus T times the change in S. But the change in H is 0. So therefore I'm left with minus T times the change in S. But that is minus R ln of xi. Therefore, the difference between partial molar Gibbs energy and specific Gibbs energy is RT ln of xi. We have one last thing we want to define, and this is mixing properties. We've seen these before. A mixing property is defined as weighted by mole fraction differences between the ideal gas partial molar property minus the specific property. Now then we're looking at this for an ideal gas mixture and an ideal gas. For volume, internal energy, and enthalpy, this is simple. The answer is 0. There is no volume change on mixing or internal energy change on mixing or enthalpy change on mixing. But for entropy, I add these up for all my components, and therefore delta S on mixing for an ideal gas mixture is minus R times the sum over all components of xi times ln of xi, natural log of xi. And the Gibbs energy for my mixture as an ideal gas mixture will be RT times the sum over all components times xi ln of xi. So these are going to be useful because they're going to be our standards for reference when we want to see whether or not our estimates are rational, or so that we can use this as maybe a starting point in a calculation. Thank you very much for your time.